Okay, so that means let me take fx equal to, let's consider this function, this proof of this. Okay, so fx equal to, now here f dash x, derivative of this function, okay, f dash x equal to, this is 0, then fx1 equal to fx2, they are equal, derivative they have. That means if f dash x, it says equal to fx1 minus f dash x2, it is given to us, and f dash x is 0 if I take, because f dash x is 0 given to us, if I take f dash x is 0, that means these derivatives are equal, so that is given to us, f dash 1 x1 equal to f dash x2. Okay, so derivatives at 2 points are equal, this is given to us. Now it means what? That means that this function, if it is 0, f dash x is 0 in this case, so it means fx is constant. This implies that if f dash, capital F dash x is 0, this implies that fx is constant. Fx is a constant. Okay, so fx is a constant. So I have to take here constant equal to fx1 minus fx2. Why? Because fx is a constant then, because f dash x is 0. The function vanishes. It says, okay, is a constant. Moreover, if two functions have derivatives that are equal for all values of x in AB, then functions differ by a constant. We know that if f dash x exists in this interval and f dash x vanishes, and then because we are given f dash x1 equal to f dash x2, they are equal, this is equal to 0 in this case, only then these two derivatives are equal. So this is equal to f dash x equal to 0, that means f dash x is 0. F dash is 0, that means fx is constant. Okay, so this implies, so f dash is constant, we have put here, therefore fx1 equal to a constant plus fx2, fx2 plus a constant. Constant may be any k or anything. So fx1 equal to fx2 plus constant. So this is, they are differing by, they have difference by a constant that is given to us. It says then the functions differ by a constant. So these two functions are differing by a constant, but their difference is equal to constant. So this is what indicated in this theorem. Okay, this is the result based on Lagrange mean value theorem. Okay, so this is these two results are based on Lagrange mean value theorem, which were left over, so that are discussed here. Now let me talk about the Taylor's theorem. Now about Taylor's I have discussed already in the brief history of Taylor that I have already described, okay, in the previous lectures, one of the lectures of previous term. So now let me take the fourth Taylor's theorem, which is finite form. Okay, Taylor's theorem. Now this is the fourth one. Taylor's theorem, which is finite form. Let me take the Taylor's theorem, or this one is finite form of Taylor. Finite form. This is finite form units. Okay. Now Taylor's theorem. What is finite form? Finite means it has some definite terms. Okay. And previously we have discussed about the infinite series. Okay. So infinite term it was, but it is basically infinite series. But for finite terms, it is mean value theorem. This is general form of mean value. Okay. Mean value theorem, which we have discussed, Lagrange mean value theorem. Okay. Then this one, Cauchy's mean value theorem, and this is a general form of these two. Okay, or it is generally used for a number of terms. Okay, so now let me talk about what it is. Now it's a more general theorem than the one of the mean value is Taylor's theorem. The theorem is as follows, as we have discussed about. If fx possesses n finite derivatives in the closed interval AB, or in the open interval AB, in the open interval AB. This is open interval because function is continuous in the closed interval, but have derivatives in the open interval, because a and b are not included here. So in the open interval, it has n finite terms, n finite derivatives, if a function given to us. Okay, the theorem is as follows. If fx and a function given, That means a function given to us possesses different coefficients of the first n orders. There are n derivatives of, or n orders derivatives the function fx is having in this interval ab. Okay. Then this term fb equal to, this we have to prove, fb is equal to fa, okay, plus b minus a into f dash a into f dash a plus b minus a whole square upon factorial 2 into f double dash a plus and so on, okay, plus b minus a whole power, let me take r upon factorial r into f r, this is r a plus and so on. Let me take n minus 1 term, this is b minus a whole power n minus 1 upon factorial n minus 1 into f n minus 1 a plus b minus a whole power n oblique n factorial into f n a. Okay, this is f n a, but here in place of a we have to prove this. In place of a or fn, if we write this function plus term, this is b minus a whole power n upon factorial n into fn. In place of a we have a plus theta into, theta into b minus a. This we have to prove. This is the last term, b minus a upon factorial fn a plus theta minus theta into b minus a, which we have just, this is in place of c. If it comes c, the point lying between ab or in the ab interval, then if it is c, then we will equate this a plus theta into b minus a is equal to c. That we have already described. That let me prove here. And let us assume that we prove this. So proof. This proof that we do here. Okay, let's consider or construct function. Let's consider a function capital Fx equal to, okay, fb minus fx. This is capital Fx, okay, fb minus fx minus, this is x, a minus x, I'm sorry, this is b minus x. This is b minus x into f dash x minus b minus x whole square upon factorial 2 into f double dash x minus, okay, and so on. This is b minus x whole cube upon factorial 3 into f triple dash x minus and so on. If I write in the same way, b minus x whole power r upon factorial r into f r x, okay, and minus and so on. This is b minus x whole power n minus 1 upon factorial n minus 1 into f n minus 1 x, and the last term I have to write here b minus x oblique n factorial into q, I have written down here, into whole power b minus x whole power n into q. What is q here? Q is a constant, okay, based on the possibility f a equal to 0. Again, as I took in the previous lecture, the f a equal to 0. On basis of this, the q is taken as constant. Q is a constant here. Q is a constant. Here Q is a constant. Okay, based on this assumption, based on the assumption based on the assumption that capital FA equal to 0. If I substitute here A, then this is equal to 0. That is given to us. So Q is equal to this value. If I substitute here 0, this is 0, means FA equal to 0. If I substitute here FA, A in place of X, it will give us F0, that means I've taken FA equal to 0, so this is 0. This is FB minus FA. In place of X, I have to substitute here. This is B minus A into F dash A minus B minus A whole square upon factorial 2 into F double dash A. Okay, and so on. This is equal to minus sign and so on. Okay, and last term, this one B minus A, let me write here all these terms, B minus A whole power n upon factorial n. Last term I have written down is into Q. Okay, so this is given to us. So, all right, so these are the functions given to us. Q. Okay, so FA equal to, so B minus A. Okay, so this is one of the points here. FA equal to 0, we are given. If I substitute here X equal to B, so it will give us FB also 0. So if this is first equation I have assumed here, let me take this first equation. If X equal to B, okay, substituting in first, okay, if X equal to B substituted in first, you will get FB also 0. Why? Because FB minus FB, all these B minus B 0, all terms will be 0. That will also be 0. FB is also equal to 0. So Rolle's theorem is the conditions of Rolle's theorem are proved. FB equal to 0, FA equal to 0. Okay. So now let me take other conditions also. So FB equal to 0. So if I differentiate, F dash X must also be 0. F dash X must exist. F dash X must be 0. Or F dash zeta or C. If I take F dash C, I'll take, then F dash C will be 0. That will also be applied. So let me take the further that F dash X also exists here. So the Rolle's theorem, Rolle's conditions are such. Let me write here. So Rolle's conditions, Rolle's theorem, conditions of Rolle's theorem are satisfied here. Here conditions of Rolle's theorem are satisfied. That means, that is, number 1, FA is equal to FB. FB. Here we have proved that FA equal to 0, FB 0. That means FA equal to FB. This is FB. Okay, second condition is that F dash X exists. Why F dash X? Because function is having n order types of differentiability or differential functions in between A and B. So F dash X exists. F dash X exists as Fx, the function Fx is differentiable n order times or n order times or okay of order n, okay, differentiable of order n or n order times or n times order. Let me write here of n order, differentiable for n times, let me take. That means nth order it is having. So function is differentiable. F dash X exists, okay, in this interval. Now let me write here. That means F dash X exists. So I have to find out then F dash X, then F dash C equal to 0. So that we have to replace here. What is F dash C? And first F dash X I have to find out from this equation. So F dash X, therefore, this implies that f dash x, if I calculate from this equation, that will give us this 0. First is minus f dash x. This will give us, check here, this is sorry only fx, f dash x. It will give us minus x. If I differentiate this first function, it will be minus 1, minus plus, so plus f dash x, plus f dash x. Second derivative will be b minus x into f double dash x. This is minus b minus x as it is. This is f double dash x. I mean, this are to differentiate by product rule. First function as it is, this is b minus x as it is. F dash is double dash x. But if I take f dash x as it is and b minus x is differentiate, then minus 1 plus that I have written first. This is plus sign. Now from this twice 2 to cancel out. This is minus b minus x, okay, and factorial cancelled out, and minus 1 is plus 1. It is f double dash x as it is. Then it will be third time, so all the terms will be, let me write this rth term, or let me take nth term, last one. Okay, this is minus sign. Next, this term will be, okay, all the terms will be cancelled out. Let me take the last, this one, nth term. This will be n minus 1 factorial cancelled out. Or before this is nth term. Nth term, if I differentiate this 2 times, it will be n minus 1. This is b minus x whole power n minus 1. Okay, upon factorial n minus 1. Okay, the previous term of this as it is. Okay, then nth term will be fn. This is differentiated. It will be fnx. This is minus sign. Second term, if I differentiate the last term, this one, it will be, so sorry, this one will be with minus sign. This term as it is, this fnth term is fnx, fnx. Okay, n times the derivative. This is different. This is negative sign. Next will be, if I take this nth derivative as it is, okay, nth function is as it is. This is fn. This is nth derivative. So n cancel out. This will be b minus. This is sorry minus sign. And before that it will be plus sign, because b minus a x is again differentiated, because n minus 1. If I take this function n minus 1 as it is, n minus 2 will be there, so this will be with a positive sign, and the last will be negative sign. This is with plus sign, and last will be negative, so this will be minus b minus x, n cancel out, divided by, sorry, this will be minus, this will be plus, sorry, this is minus, but we have to differentiate this first term. First term, if I differentiate, it will be n first, n cancel out, so factorial n minus 1, this is n minus 1 left over, and divided by n minus 1 factorial, because n cancelled out. This is negative sign, and because minus x is again differentiated, so this is plus, this is plus sign, and qn as q as it is. That the last 2 terms are taken. Okay, so all the terms like this cancel out. This one will be cancelled out, second derivative, and all terms in between will be cancelled out, and the last these 2 terms, for this is fnx, this is having qn. Okay, so this terms will be left over. So it means f dash x equal to, let me write here. Here it was fx equal to, okay, this was fb minus fx. This is the basic I have assumed. This is assumption. Now let me write here. So what is the value of this? So f dash c, if I substitute here in place of x, in place of x, f dash c equal to 0, because c lies in the interval this ab, and at c f dash c will be 0 then, because all the conditions of Rolle's theorem satisfied. Rolle's theorem are satisfied. So f dash c equal to 0. C lies in between this angle. So f dash c, if I imply here, only these two terms are left over. First let me collect them. F dash x, after that I will apply this f dash c equal to 0. First let me write here what is the left over. So f dash x is equal to q, I have taken, sorry, b minus x whole power n minus 1 upon factorial n minus 1. I have taken common. So left over term will be q minus fn x. This we are left over. Okay. Now this let me rub here. So okay, the last term I have rubbed here. This is bit minus sign b minus x whole power n upon factorial n into q inverse. This is the first equation, which is not to be eliminated. Now this is the question left over. Now if I substitute f dash c, that means f dash c equal to b minus c oblique n minus 1 factorial. This is b minus x. Okay. So here c I have substituted here this n minus 1 factorial upon n minus 1 into q minus fn into c. F dash c equal to 0. Why? Because f dash x exists. So f dash c equal to 0. F dash c 0 implies that q equal to fn. So this is n of some fnc. So here q is equal to fnc. We have obtained that q equal to fnc. So final answer is that q, in place of q which was constant, we have to substitute q fnc. Therefore this implies that what is fx here final? Fx, the result obtained is fb minus fx minus b minus x into f dash x, okay, minus b minus x whole square upon factorial 2 into f double dash x minus and so on. Now last term is in this equation we will obtain, okay, q, in place of q we have to substitute all terms in between will be there, this b minus x whole power r upon factorial r into fr x minus and so on. The second last is b minus n minus 1 upon factorial n minus 1 into f n minus 1 x minus sign. This is b minus x whole power n upon factorial n, this factorial n into q, that means f and c. So in place of c we can substitute a plus theta into b minus a, which I discussed just previously in this second result. Okay. So in place of c, if I substitute, we can obtain this result a plus theta b minus a. So in place of c is the same result, fb is equal to, okay, this was the result given to us, sorry, this one, okay, fb equal to fa. Okay, if I put f dash x equal to fx equal to, in that case fx was this whole value q and c. Okay, so fx equal to fb minus fa, fb minus fx. If I then, okay, replace fb equal to fa plus b minus a into this f dash c, and then q and c, final result is obtained. So q value is, if I replace here x by a, so then that result will be obtained. Okay, so that result can be obtained here, fb minus fa. So in place of x, this is fb equal to, this fb will come here, this is fa plus b minus a, and this fx equal to 0. So fx, this we have taken here, fx will do fb minus ba. If I just replace this question, okay, so final result is obtained as, let me write here, fx we have taken, so final result is that which is obtained, and value of q is obtained, so that value is, let me substitute there, fb, so final, this result is same, fa. So if I replace, okay, x by this x by b. So b minus x, so x by a. So f a, x by a, if I replace, so we will obtain f b is equal to f a plus, this is b minus a whole square. So b minus a into f dash, b minus a f dash a. This x has been replaced by a. But in the same result, x I if I replace by a, this whole result will be obtained. What is that? F dash a, then b minus a whole square upon factorial 2 into f double dash a plus and so on. So in place of x, we have to substitute here a. So the same result will be obtained. Okay. In this case, okay, fa, but fa equal to 0. So f0 in capital fa0 has been substituted here. So f be taken to this side. This f we were having here fa. Okay, equal to fb. This was there minus fa we were having, because in place of x we have substituted this equation. This is capital fa, but fa equal to 0. So in this case, fb can be taken to this side, or all these terms will be positive. Then the same result will be obtained. So fb equal to, all these negative terms will be positive to that side. So fa minus, this was b minus a, because in place of x we have to substitute a. Okay, so this is minus, we write here complete equation which I have obtained here. B minus a into fa, sorry, f dash a. This is minus b minus a whole square on factorial 2 into f double dash a. So in place of x, substitute a. We can obtain this whole result. Okay, that is minus b minus a. Okay, let me write here minus sign, three results, and this is b minus r on factorial r, b minus a into f r a minus and so on. This is b minus a whole power n minus 1 upon factorial n minus 1 into f n minus 1 a. Okay, with minus sign, b minus a whole power n upon factorial n into f n. C, in place of c, we have to substitute a plus theta into b minus a, because I just assume that c minus a upon b minus a equal to theta, where theta is less than, greater than 0 and less than 1. Okay, so in place of c, from this equation, theta into b minus a plus a, we have substituted in place of c. That is minus sign. Okay, so if fa equal to 0, I substitute this 0, because fa is 0. Take this fb to one side and all negative terms to that side. Then this finite form will be obtained. Finite form, this fb equal to this. Let me write here. All the terms will be positive. Other than this fb, take all the terms to this side. So this is fa plus b minus a f dash a plus all these terms plus, let me write here dots. Okay, this is b minus a whole power r upon factorial r into f r a. Okay, plus sign dot, three dots, and this is plus b minus a whole power n minus 1 upon factorial n minus 1 into f n minus 1 a, plus this is b minus a whole power n upon factorial n into f n a plus theta into b minus a. Okay, so the final result is obtained. So this is the finite form known as Lagrange mean value theorem. Now, if I replace b minus a by h in this case, that is another form of Lagrange, sorry, this Taylor's theorem. What is the, if I substitute here b minus a, the integral equal to h, b minus a equal to h. So then we will obtain here b equal to a plus h. This is f a plus h equal to f a, okay, plus h into this h, b minus a is h into f dash a, plus h square upon factorial 2 into f double dash a, or a if it is replaced by x, that we will talk about, and if this is 0, then Maclaurin's theorem is obtained. This is f double dash a plus and so on. This is h whole power r upon factorial r into f r a. Okay, so this of b minus a we have substituted the h only. So h is this. So this is plus and so on. Number of results are obtained. This is Maclaurin's term as okay. 0. This is hn or h. Let me write here last term. Hn upon factorial n into fn a plus theta into h. Why? Because b minus a is h. So this is theta into h. This is the finite form of another form of Taylor's theorem. Okay, so finite form fa plus h equal to this one. If I replace here a by x, okay, in this case b by x, this will be fx equal to, and this is by h, b minus a equal to h. Okay, this is h here. So b by x if I replace only, then also another form is obtained. So this is how we can obtain this fx equal to, or fx equal to, if in place of b if I substitute x, this is fx equal to fa plus this b minus a, in place of this x minus a will be obtained, and the result is obtained. Okay, so this is a number of forms can be obtained. Therefore, this final result has been obtained because capital Fa equal to 0. After substituting that, whatever we assumed, this whole result is obtained. This is how Taylor's series, this is known as Taylor's theorem. Now let me talk about what is Taylor's series. Now Taylor's series, and there is another form of Taylor series. So what is Taylor series? Let me talk about that and the final topic. So the question is, what is the Taylor series? Now fifth, Taylor series. This is final result, final question. Taylor series here. Now the finite series which we obtained here, if up to n, there are n plus 1 terms here. If up to n terms, from initial to n terms, I have to take that as Sn series. So the sum of the first n terms, if I take as it has been taken, Taylor series, it will denote the sum of the n terms on the right hand side of this equation, this right hand side of this n terms for this by Sn. Okay, and the last term, which is n plus 1th term, this is the last one. This has Rnx, okay, or capital Rnx. Then the Taylor series is obtained. So this Taylor series is Snx plus if the first n terms of the right hand side